He's about to take his finals next week. So, a bit of a digression, and he travelled up on the train from London. He cycled from Ipswich Station to Martlesham. How many of the rest of you cycled here this morning?
In my dreams last night.
So hence, as we talked earlier, having a younger member to come along and talk to us is much appreciated, and certainly, as I say, from a timing perspective, we really appreciate William coming today. He gave this presentation, or a version of it, at the RSGB convention in October last year, and having seen William in action, having watched the audience response, I immediately said to him, please can you come along and present at the round table as well, because you get a real microwave audience learning all about from death rays to dinner. So William, the floor is yours.
Thank you very much, and good afternoon. Given the audience today, I've made the bold decision to drop my first slide entitled What Are Microwaves? And we'll go straight into the body of the presentation. I should say that when I first gave this talk, it was for a competition, or a version of this talk, and one of the judges very cynically at the end asked, William, what do you think this presentation aimed to achieve? Well, I couldn't really think of any answer other than to educate and perhaps, or to entertain and perhaps even to educate, so I hope you'll take it in that spirit. And I've given myself a much easier task in that I have no live demos and I'm not really aiming to get anything desperately complicated across. And so we'll begin with some vector calculus. No, don't worry, just for show. And we begin with a little history. In fact, the whole talk is a little history in a sense. Many of these figures, hopefully, are familiar. At the far left, we have Michael Faraday, who is widely known as the father of electromagnetism. He is quite well known for being unable to do even basic algebra, but he was a great experimentalist, and he came up with quite a lot of useful stuff. In other words, kicked the whole thing off. We then move on to Maxwell, not very much later, in the 1830s, who crunched it all down into a set of equations, which is remarkably useful if you actually want to calculate anything. And we then come to Oliver Heaviside, who in many ways is a rather heroic figure. I take it you've all heard of Heaviside, have we? Yeah, jolly good. Of course, gave his name to the Heaviside layer in the ionosphere. He invented coaxial cable, and he crunched Maxwell's roughly 20 simultaneous equations into this set here. And this despite having about 2 years of school education from something like 12 to 14. So he didn't do badly, really. We then come to the figure on the right. Who's heard of Jagadish Chandra Bose? Ah, less well known. I'm pleased I'm doing something then. Good. Chandra Bose was born in India and came to UCL in the 1890s. Or 1870s, sorry, to study medicine. And within a year, somehow he ended up at Christ's College, Cambridge. I don't really know how that happened, but, you know, move around. And he ended up as a natural scientist. He then went back to Presidency College, Kolkata, and immediately became a professor of physics. So promotion in academia was rapid in those days. And he was lectured while he was at Christ's by Rayleigh, who, of course, Lord Rayleigh of Rayleigh scattering and so on. And anyway, he ended up as a professor of physics at Presidency College, Calcutta. He taught S.N. Bose, who is quite well known for Bose-Einstein statistics, if anyone's quantum mechanic here. Quantum mechanics, yes, jolly good. But more importantly, to us at least, what he did in the bathroom, or rather in the cupboard in the cupboard next to the bathroom, which he converted into his microwave laboratory. And in the microwave laboratory, he obviously, very high investment places. He was the first person to use a semiconductor junction to detect radio signals, which pretty ubiquitous nowadays. He made spark gap transmitters and dielectric lenses and all sorts of fancy things that we would recognise as part of the modern microwave canon for frequencies all the way up to 60 gig, which is really quite phenomenal when this was late 1890s, early 20th century. So very impressive and really not surpassed for the next 60 years. A lot of this talk is unashamedly focused on radar and that kind of thing, and it is with this in mind, perhaps, that we come to Christian Hulsmeyer, who is relatively well known as the father of radar. He was deeply affected, apparently, by a collision between two ships on the River Weser near his home in Germany, and he decided that he should do something to stop it, and he came up with this idea of the telemobiloscope, as he called it, and here it is, or a patent for it, and it's a rather splendid thing. I mean, you can recognise, you know, the vague outline. You've got some sort of rotating antenna, and anyway, the idea was it would send out radio signals, or it had a very, of course, the first thing to remember when you're marketing something is to give it a snappy title, and he called it Hertzian wave projecting and receiving apparatus adapted to indicate or give warning of the presence of a metallic body such as ships or train in the line of projecting of such waves. Anyway, it was a bit of a flop. By all accounts, it worked to some extent. He put it on a bridge and it detected a ship underneath, at least so the legend goes, but it didn't really take off. And in a refreshing change from most of these genius inventors years before his time, he ended life very comfortably, having made other inventions instead in the fields of boiler making, metallurgy, and light bulbs. So, a man with 160 patents over the course of his life, and at least some of them worked out very well for him, but the telemobiloscope was largely lost to history for some years to come. But nonetheless, people were starting to think about how you could detect things at a distance, and specifically aeroplanes, because of course we'd seen the advent of aerial warfare in the First World War with zeppelins and to some extent fixed-wing aircraft as well, and at least over distant countries. And there was some concern about this, understandably perhaps. The Americans were researching radar in the 1920s, as were the Italians, the French, the Russians, the Japanese, and so on. Everyone was at it over at least the period from 1920 to 1945, at some point within that range. And the British had the idea, shortly after, in the 1930s, I believe, that they might be able to detect aeroplanes by listening to them. And to that end, they built, some of them are still there in Kent, these enormous concrete mirrors as an experiment. You could put a microphone at the middle and listen very, very carefully, and you could hear the aeroplane coming with a full 1 and a bit minutes notice. Unfortunately, at 250 miles an hour, that's not much use, really. And by the time your aeroplane's taken off, it doesn't do much for you. But this did come in handy at a later stage in our story, because it also got the RAF and similar bodies thinking about how they could process information from a network of sensors and simplify it, filter it, and give it effectively to flight crews. And that is what led, in some senses at least, to the Dowding system and all of those rooms in war films and so on where you see the wafts pushing models around on tables, the plot rooms. The other thing that everyone is famously very concerned about in this world is a death ray. And there was a plethora of different death rays invented, including by a number of well-known names. In fact, the Air Ministry got a bit tired of having death rays offered, and they said, well, if you'd only give me, a few £1,000s, these inventors would say, then I will give you a death ray. And the Air Ministry solved this problem by offering an interim solution. They said, anyone who can kill a sheep at 100 yards will have a prize. And one civil servant at the time records that the death rate of sheep was unaffected. Nonetheless, there was some concern after a probably misinterpreted press release by Hitler in the 30s, 1935. And this man, Sir Robert Watson Watt, once again, hopefully quite a familiar figure, because he really he coined the term ionosphere. So for any HF people, it's always amused me, by the way, that the UK Microwave Group has its weekly net on 80 metres. So for any, I know you're all HFers and MFers, really. So quite a significant figure. And he passed it on to his assistant, Arnold Wilkins, whose name pops up quite a bit in the subsequent years of radar development. And he did some calculations which we can perhaps sort of try and synthesize here. If we assume the pilot is a sort of blob of water of about 70 kilos, and let's be generous to start off with, because after all we're only in the initial stages of development, and say he's sitting a few hundred meters away, parked, just for convenience, how long might it take us to heat him up by 2 centigrade, which is certainly going to make him uncomfortable, if nothing else? We can do some calculations, and we find that if we have an isotropic antenna that's sending power out equally in all directions, then we need 4.4 gigawatts, which is quite a lot of power at RF in 1935. It's quite a lot of power now, actually. Not least because presumably there's going to be an operator somewhere near the antenna, and if it's isotropic, he is also going to be objecting to some extent. So we might need some antenna gain, and if we reckon we can maybe optimistically put out 50 kilowatts CW, which at the time is going to be a challenge at any frequency really, we can manage with a mere 49 dB of gain. Of course, at the time, very high frequency. These are the days when VHF really meant very high frequency, 30 megahertz. Gosh, who could imagine such a thing? And 50 kilowatts at 30 megahertz, well, you're going to have a job getting a 50 dB gain antenna out of that, aren't you? But there was the question of reflected power, and that has a little more promise in it, perhaps. Some of you may be familiar with this derivation already. We're not going to dwell on it in any great depth, but if we work down from the top, if you consider the power radiated from the transmitter, radiates out in some sort of a sphere with a gain, so we may have a slightly directional antenna to avoid cut the amount of power we need, and then if we imagine, just for the moment, that the aeroplane reflects all of the power, for convenience's sake, in every direction, we can work out some equivalent term for the power coming back. And we make a little substitution because the power coming back is going to be in terms of power per square meter, and we want power output. We want a power in watts, not watts per square meter. So we make this convenient little substitution, and the enthusiasts in the room can work out where that comes from with a very neat little thermodynamic derivation and answers on a postcard after lunch. A short quiz at the end of the talk, so I hope you're all paying attention. No. Anyway, we end up with the radar equation, which is rather convenient, except for one thing, r to the 4. In other words, if I double the distance to my target, I increase the amount of power needed to get the same return by a factor of 16. That's a poser, that is. And there are a few other issues as well. Your antenna gain, and indeed your receive antenna gain, are directional, and of course the cross-sectional area of the target, which we've just called I should really called it AT there, but never mind, is also a function of which way the aeroplane's pointing and all sorts of things, what it's made of. If it's made of wood, it might not have a very good cross-sectional area. So all of these things are really variables, and as I say, anyone keen can try and work out the effective area. But anyway, we got to the stage of being able to do an experiment, and the RAF deployed a cutting-edge biplane to the site of the British Empire Service Shortwave Broadcasting System in Daventry, which of course was there not to broadcast really to the Empire but to the people running the Empire, and keep them all fed with the BBC and the voice of civilization, and so this was rather conveniently at about 30 megs. Oops. And they set up some rather crude antennas in a field, and effectively it's now what we'd recognize as passive radar. They had one antenna which was receiving, or they had an antenna which was receiving the signal directly from Daventry, and another one, or possibly the same antenna, I'm not quite sure actually, which received a signal reflected off the aeroplane. And of course there's a phase shift because there's a difference in the length of the path. One's coming directly, one's going up and then down. And from that they had a little blip that moved along an oscilloscope, and the one or two officials, I somewhat imagine them dripping wet and in Wellington boots, but I've no actual substantive evidence for this, in this field, probably rather muddy in Daventry, were apparently very impressed because they coughed up a lot of money, and 4 years later, by Good Friday 1939, the rather famous chain home system came online, and this is really quite a development from a shortwave transmitter and a single aeroplane. We couldn't really tell where it was coming from or anything like that. By this time, we've got the power up, 100 kilowatts. This is pulse power, right? So there's probably 100 kilowatts continuous wave, might have been taxing at the time. 100 kilowatts pulsed, and we have these antenna towers here. These are 350 feet high, steel lattice masts. They are not particularly directional. They radiate a signal in all directions. It's a bit like a massive floodlight rather than a pencil beam torch. And then, in order to get an idea of where the aeroplane actually is, rather than just that there's one in this volume of sky somewhere, we have a set of 4 240-foot wooden towers. Massive, massive antennas, and obviously not in the slightest bit portable, really, which we use a mechanical phase shifting arrangement to DF the aircraft, effectively, and in the time-honoured fashion. And the analogue, I suppose, really is a 4-square array, as often seen on HF setups today. It's a phased array antenna. And we can work out, we've probably got a range of about 100 kilometres, which is quite respectable. You know, that's enough warning, really, to get an aeroplane off the ground and up to see it. And, of course, the basic concept of most of these systems, certainly this one, was that you sent out a short pulse, you measure the round trip time to the aeroplane, and because you know how fast light travels, you can work out how far away the aeroplane is. And if you can, with this phased array mechanism, measure the angle, and by sweeping the frequency and using the response of the curtain antennas here and all sorts of other clever tricks, you can guess the elevation, you actually can begin to fix an aircraft in 3D space, which is rather convenient. And so, of course, the theory is that, you know, these very brave chaps would go off and sort it all out. And by 1939, we have this coverage here, and they'd also introduced chain home low, which was a higher frequency system aimed at stopping aircraft down to about 500 feet. And as you can see, this actually covered the vast majority of the threatened coastline, so it should all have been fine, really. And then the Germans and the Luftwaffe came up with a bit of a devilish scheme, which was to fly at night. Now, it turns out, unfortunately, that if you're in an aircraft with no assistance, you can see a typical wartime bomber from about 300 meters away. Now, chain home was not that phenomenally accurate, and also, frankly, navigation wasn't that phenomenally accurate. To place an aircraft less than 300 meters from an enemy bomber in 3D space as well, remember, was a phenomenally difficult task, and really, they'd have been lucky to get anything. What was really needed was airborne radar, and this is very difficult, and Watson Watt had a splendid engineering paradigm. Give them the third best to go on with. The second best comes too late, and the best never comes at all. This is something which I think can be readily applied to amateur radio in general. Anyway, this was, you know, pushing on for what we now recognise as VHF, very much 193 megs, you know, that's quite respectable. And once again, it first flew on the 1930s Handley Page Hayford biplane. And on this, they strung an antenna between the landing gear, fixed landing gear of this aircraft, and sent it up, and it was established to work. It was based on a television receiver, an IF 45 megs. And there were a few problems with this. The principal one was the range. And you might be thinking, well, they couldn't get the range up enough. Quite the opposite, actually. It was the minimum range that was the problem. Because they'd squeezed the pulse down a lot, but the trouble is this television receiver would tend to ring for some considerable time after each pulse. Long enough, in fact, that the minimum range was about 300 meters. So unfortunately, as you would fly in towards the target, just as you'd be starting to look out of the window for them, suddenly you'd lose it on radar entirely, which was of limited use. They managed to solve it eventually, and they got there to a sizable extent, but it was debated, and this is a highly contentious point, I think, among historians in the field, but it's definitely my perception that it had less of an impact on the Blitz than it could have done had it come in just a little bit earlier, because by the time it was introduced in serious quantity, the amount of time left for training was pretty much nil. But nonetheless, it surely made some contribution, and it was very groundbreaking in its way. What we really need, of course, is to get the wavelength up, because your antenna size is roughly proportional to wavelength. You want to put it on an aeroplane. Aeroplane designers hate having big things on aeroplanes because they're heavy and draggy. But radar engineers want big things on aeroplanes because they want to be able to see the target. So this has always been a bit of a trade-off. In fact, even in the current defence sector, it comes down to, well, what do you mean I can't have a carbon fibre radome? What do you mean it's conductive? No, well, such is life. But anyway, yes, so we want to squeeze down the wavelength, and of course, the magnetron story is quite well known. Do I need to go over it today? Should I? This is the cavity magnetron as developed by Randall and Boot at Birmingham University in 1940. The magnetron itself had been around for years, and the Germans, in fact, had big advances in it. Dr. Hans Hollmann in 1935 in Berlin patented something quite similar, although it didn't really work anything like as well. And the genius of Randall and Boot was in solving the thermal issues. Previous magnetrons heated up far too much, and so they couldn't be run at high power for long, otherwise they'd burn out. They made it out of this rather delightfully milled, I'm sure there are lots of machinists in the microwave community, rather delightfully milled block of metal, and funnily enough, that's quite good for dissipating heat. Anyway, I'm not going to explain the workings of the magnetron because I don't really understand them well enough, but it's all to do with magnets and electrons whizzing around and that sort of thing, so you can work there. That's another one for the enthusiasts to explain to me later. But anyway, there are some issues with it, and that's why the Germans didn't really think it. They thought it was totally useless for radar, because every time you turn it on, it jumps in phase. It's not really very frequency stable, because especially as it heats up and cools down and so on. It's just a bit difficult, really. And also, it's an oscillator. You can't amplify a signal. It has to be, what that puts out is pretty much what you're going to get. And all of these were problems for the British as well. But our klystrons, our vacuum tube-based amplifiers, were nowhere near as good as the German ones, so we didn't really have anything like as much option. And when Randall and Boot came along and suddenly said, we can give you 10 kilowatts at 10 centimetres, who were we to say no? Anyway, this went to America, and good grief. And my images have all been shunted around. I don't really know how that happened. Never mind. You see the disembodied head there of Sir Henry Tizard, who is quite well known for the Tizard mission, in which a number of British technologies, the jet engine and the magnetron, to name but two, were taken over and effectively given to the US in exchange for assistance in manufacturing them. Because really, sure, we knew how they worked, but we couldn't make as many as we needed at the time. And this is, once again, something of a controversial move, but it seemed to work out quite well. And one American negotiator apparently later described the magnetron as possibly the most precious cargo ever brought to our shores. Anyway, they wanted to set up a laboratory at MIT to research it, and they thought, well, we don't want to call it the microwave lab because then any spies would be able to find out what it was about. So we'll call it something that couldn't possibly have a warlike. What about the radiation lab? Nobody would ever use anything useless like nuclear physics for warfare. So it was that the radiation lab came about, and a lot of very, very clever people were brought together. They brought out, in fairly short order, a 10 gigahertz version of the British magnetron-based radar. Our one worked at 3 gigs, the American one worked at 10 gigs. And they were very successful. In fact, it was really the combination of the magnetron-based radars and a few of the earlier airborne intercept units which saw the successful fight in the War of the Atlantic against the U-boats, because finally they could be detected from the air at significant range. There's a bit of an entertaining story about this, actually, talking as we were, I suppose, to some extent in the earlier talk about harmonics and spurious emissions. The Germans had a detector for the 193 megahertz coastal command radars, and it was called Naxos. And it was unfortunately rather effective. And every time the British aeroplanes fired up, or the Allied aircraft fired up their airborne intercept radar, the U-boats would detect this pinging and immediately think, I think we might go for a little dive. And by the time the aircraft arrived, they'd disappeared. Until a mechanic was captured by the Germans, and he was very quick-witted. And he was interrogated about this, and he said that the British had a way of homing on the Naxos radar detector. Of course, we'd never had anything of the sort. It was a total fabrication. But the Germans then, being very methodical, took it to their test labs, and they thought, my goodness, actually the local oscillator is leaking out of this thing pretty badly. So they took it out of commission entirely across the fleet, which gave the British time to bring out H2S and H2X, which they had no way of detecting. So that was quite a successful ploy, really. I gave this talk relatively recently at CDARC, Cambridge District Amateur Radio Club, and Andrew Holm, who is a great, a prolific producer of a lot of quite interesting projects, emailed me afterwards and said that he thought this should be in it, and I rather agree. Wireless set number 10 was an 8-channel microwave 4 to 8 gig phone link that was developed during the war by the British and deployed in Germany shortly after the invasion of Germany to provide communications across the country. And it had 8 channels per link. It had about a 30 dB gain antenna, a big dish, and it had a number of interesting firsts. It was, they think, the first pulse-modulated phone link, probably, or RF phone link anyway, and it also had the first, what we would describe probably as a low-noise block in modern satellite TV parlance, in that it had the LO and the mixer and the IF amp all in one box, and then a signal at IF coming out. And there's a paper, you can read that. And once again, this has changed since, oh dear, never mind. This was the rather, I thought you would have to see this. This was the rather splendid tuning arrangement they had in the mixer, and it looks really like a lathe, doesn't it? It's a remarkably sophisticated mechanical tuning setup. And then in the bottom here, under the text, you can see this was the whole station mounted in a trailer, and this is inside the switchboard, so the operator could connect you. And yeah, quite impressive technology, really, when you think that was ready for 1945. Anyway, we come to the end of the war, which is a bit of a relief for everyone involved, I think. And don't worry, I am getting towards the end of the talk as well, you'll be happy to hear. And we come into a variety of other applications for microwaves. Of course, communications we've just started to hint at, really. And these were the days, you know, when HF was one of the preferred means of long-distance telephony, and so forth. And so radio really was at all frequencies and in all uses. And of course, standing here, I can't fail to mention the BT tower. Which nowadays is rather denuded of microwave dishes, but at the time, or at least back in the days of the microwave backbone and microwave links around the country, was festooned prettily with quite a lot of them. This is Telstar, as some of you may be aware. And this is another invention of the University of Birmingham, 1943. I have to look at that, sorry. The travelling wave tube, and another thing commonly used in microwave power amplifiers today, and invented, in fact, by, I think, a German exile during the war, I seem to recall. Rudolf Kompner, I think, was the name, but I might have gotten that wrong. So once again, a bit of a, yes, classic case of perhaps the Germans' policy of persecuting lots of people working against them there. Starfish Prime deserves a mention as well. Starfish Prime is nothing to do with microwaves. It was a thermonuclear bomb, and they tested it, detonating it at an altitude of about 250 kilometers in the same year as Telstar. It's totally unrelated, you might think. Unfortunately, Telstar then flew through the radiation cloud in orbit that this had produced, and promptly died, as did one of the first British satellites. And so it pleases me somewhat, in many senses, to say that the US Army, who were also involved with Telstar, are perhaps the only people ever in the history of scientific research to have shot themselves in the foot using a megaton thermonuclear weapon. I promised death rays to dinner, and here it is. This is the radar range, 1946, and it was invented by a chap called Percy Spencer, who was a radar engineer at Raytheon. He was wandering around the test lab one day, as you do, when he noticed that a peanut bar in his pocket was beginning to melt. Now, I have to say I have some concern about the rest of his anatomy, really. I should say the bits principally affected by microwave radiation are those with low blood flow, namely the eyes and the testicles. I'm afraid I've no record of his ophthalmological health, but he did have 3 children. So anyway, that seems to have gone all right. But he then experimented with peanut with peanut bars and with popcorn. And there is a patent from the well-known defence company Raytheon for microwave popcorn, circa 1945. He also put an egg in a kettle and poked a magnetron down the lid of the kettle and saw what would happen. And of course, anyone who's ever microwaved an egg is aware that it's not an entirely good idea. One of his colleagues thought this was a totally stupid idea, this microwave cooking, and he peered down the spout, apparently, at an inopportune moment. And never before or since, really, has anyone quite so literally had egg on their face. Anyway, they went on to release the very affordable $1,295 home oven, which is only $12,000 in today's money. And the Amana name, which the Raytheon system became, is still going today. It is a bit cheaper now. And they have a fan site, the Amana Radar Range. I'm afraid, you know, even in a group of radio amateurs, I don't feel quite ready to show that. But nonetheless, I thought that was rather good. And there's a splendid advert, which I don't think I have time for, featuring Barbara Hale telling you about how you can cook a whole roast dinner in your Radar Range oven. Everyone here knows about transistors already, so I think we can probably skip that. And we'll whisk over these. Specifically, the idea that now, a few more recent developments, this is probably best termed. The idea that you can measure the Doppler shift of a signal. So when you irradiate a moving target, moving towards you or away from you radially, then it reflects the signal back with a slight frequency shift. And if you draw it out on paper, it all makes perfect sense because the crests of the waves get close together or further apart. I'm not sure it's rigorous, but it works for me. This is termed Doppler shift. It's been known about for much longer than anything to do with radar. But you can use it very conveniently for radar because you can measure the radial speed of objects, whether that is an aircraft or a storm cell. And it also is quite good if you want to suppress clutter. For example, if you're looking at the perimeter of an airport and you want to detect whether people are moving around on it, you don't really want to detect the metal fence, which is there all day, every day. And sure enough, that's not going to give you a Doppler return. So you can ignore that completely, and things that are moving you can pay a bit more attention to. Next subject. These are now a set of somewhat disparate but quite interesting areas. The Rayleigh Criterion. Who's heard of the Rayleigh? Anyone heard of the Rayleigh Criterion? Lord Rayleigh? This is principally in astronomy. The idea is, if you have a light source and a slot, you get a diffraction pattern. So the light spreads out through the slot and interferes. You get an interference pattern a bit like this in amplitude. If you put it through a circular disk, it looks more like this. And of course, we do quite a lot in astronomy. You do quite a lot of looking at light sources through a small disk. The disk can be your eye, it can be a telescope, whatever you fancy, but ultimately you get a diffraction pattern. And the problem is that sometimes the fringes interfere if you're looking at too small an object or using too small a disk. And once you're getting interference from that second fringe, you can't resolve the object. So this is known as the Rayleigh Criterion, after Lord Rayleigh, who thought of it, presumably. Only assume. Thought of lots of things, so it's probable he did. And we have as you can see, I'm an expert in graphics design, so I've drawn this wonderful diagram for you. But anyway, this is Sir Martin Ryle, Golf 3 Charlie Yankee, and he was for a long time president of the Cambridge University Wireless Society, whose jumper I'm sporting today. And his contribution was the idea that if you use lots of radio telescopes spread over a wide distance and some clever signal processing, you can stitch the images together and use it as if you've had a massive radio telescope, far bigger than you could ever feasibly build in one antenna. And I wasn't going to present this slide, and then recently something happened in the news which I thought deserved inclusion. And so this was taken using, this image is by the Event Horizon Telescope Collaboration, a famous image of a black hole. It's been making the news headlines for a long time, perhaps because all the other news seems to have fallen into it. And this is once again aperture synthesis, courtesy of aperture synthesis, and thanks to our friendly radio amateurs development in the distant past now, really. And he won the Nobel Prize for that, as did his colleague Tony Hewish. I'm nearly there. Promise, you can go for lunch soon. Anyone want to run? No, good. Right. We saw a bit about how you can avoid having a rotating antenna with chain home. There it was because the antennas were so massive that the only way you could rotate them really was to knock them down and build them somewhere else. And they did fall down occasionally. They had a special strengthened specification for the west coast where the storms used to roll in and blow them all over. But generally, we don't really want to have a big rotating antenna on fast jet aeroplanes nowadays. It's a bit inconvenient. And so you don't want an antenna like this. You want something stationary. And if you have a stationary antenna, you have lots of different antennas, and you feed them all with a slightly phase-shifted version of the same signal. By controlling that phase shift in an intelligent way, you can, of course, steer the beam. And nowadays, because of the transistor slide I skipped earlier, we can make lots and lots of amplifiers in not very much space, and we can make them for very high frequencies, which is exceptionally convenient if you want to pack them all into a small area. Because the frequency is high, the antennas are very small, which means you can have lots of them. And this, once again, the images have all moved around, but never mind. This is a phased array radar. You will note the photograph is in black and white, which, given I've just been telling you how it's all thanks to transistors and modernity, might seem a bit odd. But just to put this in context, this is a World War II German phased array radar, probably really the first ever in the modern sense. And it had a mechanical phase shifter. The British nicknamed it hoarding. I can't think why. It was really quite impressive for the time. This was with a big mechanical phase shifter, a bit like a pair of bellows, in which a metal arm could move round and change differentially the lengths of lots of different tracks with slotted waveguides. This is what it looks like now. And this is a transmit-receive module, as it's called, from the Eurofighter Typhoon's radar. So this is 64.5 millimeters long, under 6.5 centimeters long. And just to give you an idea, the signal comes in here and it gets split and phase shifted. It gets amplified. These are a pair of power amplifiers combined together, and it goes out to the antenna. The signal then comes back, gets filtered and amplified and so on. It gets phase shifted a bit, and it goes out into a manifold where it gets processed together with all the other data. And because you can control the phase shift on each module using these control pins, you end up with a signal, you end up with a phased beam. And one of these modules, well, there are 1,424 of these modules in a Eurofighter radar, which comes to €1.5 million. And I hope you like it, because that's 1.5 million of your euros. And this is it in place on a representative aircraft, apparently. Finally, on the cheaper end of the scale, I should say about the other one, there are some quite impressive stats, actually. These are from the F-22 radar, but I'm guessing it's pretty similar. They claim 120 miles against a 1 square meter target. Remember chain home, we reckoned we had about 100 miles against a 100 square meter target. We can put out 20 kilowatts of peak power, which is less than chain home, in all fairness, and admittedly it is a bit less than 350 feet high times 4 masts plus receivers. And we can scan from side to side over 120 degrees in about 1/100th of a microsecond. 10 nanoseconds to scan from one side to the other. And this is the real advantage for fighter jets and so on of phased array technology. You don't have to wait for that antenna to swivel round, because, of course, while it's doing that, there could be a missile coming at you from this side that you'd rather like to know about. Anyway, we come to this, and this is, in many ways, more interesting, because this is actually, well, does anyone have an idea of what this might be for? This is a 16-channel phased array receiver. 77 gigahertz. Yep, car radar, yes. And so this is to go in the adaptive cruise control, perhaps, or reversing sensors, or something like that, of your high-end car. Give it a few years, and it might not be just the Mercs and BMWs and so on. As we come to an end, I know I mentioned death rays earlier, and of course you can trust the Americans to have a go at it. And this is the current version. It's not in black and white.
It doesn't kill, but it does make you uncomfortable.
Well, as I say, the Pentagon's pain, and as I was going to say, death ray is a bit of a generous term. We have a journalist here, and I mean journalists, you know, commendable types in many ways. I got blasted by the Pentagon's pain ray twice. Well, I think that confirms it's not a death ray, so we move on from that. But they have, I believe it has been shrunk down a bit now, but it's really quite an impressive system. And putting out 100 kilowatts continuously at 95 gigahertz.
No.
I believe, yes. It's a version.
Very short.
Really?
Very
Well, it must be fairly. It can't be that short, otherwise it wouldn't give you all the pain, surely. Oh, I don't know. Anyway, I take that. All right, I shall retract that. I did think there were phenomenal statistics at the time. Unfortunately, my sources don't run to anything quite that sophisticated. Anyway, finally, I am wrapping up. I promise. We're coming towards sandwich time. What might happen in the future? Freescale keep going on about solid-state microwave cooking, which they're very keen on, principally because their transistors are very well suited to it, I suspect, but also it is genuinely possible nowadays. And their demo application is a microwave oven you can take camping with you. Unfortunately, the battery life is a bit dodgy at the moment, so I beg leave to doubt as to whether it's really a practical application for now. But the real opportunity for that is in commercial microwave ovens, where the magnetron packs up after a year or two. You want a new one. Instead, if you have a set of solid-state transistors in there, as long as you've controlled the temperatures right and you're not driving them too hard and so on, should last pretty much as long as the restaurant does, which in some cases might be less than a year. I suppose it depends how thoroughly they do the cooking. Anyway, also in the cellular communications world, we're seeing more and more complex modulations thanks to software-defined radio and so on as well. LTE, which most of us use now for 4G, is 64 QAM, and each of those, and that's on 1,200 carriers, 1,200 carriers over 20 megahertz. All of those are uncorrelated, which means sometimes they spike together and sometimes they don't, which means the ratio between the biggest signal you put out and the smallest signal you put out is enormous. And the problem is that if you're running your power amplifier so that it's constantly driven, then all of this power outside the blue sinusoid gets wasted, effectively. So something that's coming up, and indeed is already in use in some areas, I believe, is envelope shaping, where you drive your power amplifier with a varying bias, effectively. Then everyone wants to make things cheaper, and everyone wants to do it on graphene. I'm forced to conclude that graphene, I think, offers promise in the higher frequency ranges. I have my doubts about some other applications. This is really an aside. I nearly bought, just for amusement value, a bicycle tyre the other day that promised to be enhanced by graphene. It said in the blurb that it gave it very high electron mobility. Now, I can only assume this means that the bicycle wheel will go round very quickly because all the electrons are so mobile they want to get where you're going. But anyway, we'll leave that aside and I will finally wrap up. And we've run through from the Jagadish Chandra Bose in the loo, or next to the loo at Calcutta, with his 60 gigahertz waveguide. We've gone back a bit to mere sort of tens of megahertz, where we couldn't make a death ray. We've invented radar, which was very clever of us, and everyone else who did it, of course. We've done a number of other things with radio, and we've looked at some stars. We've looked at a black hole, which I wasn't really expecting when I first wrote the talk, but it's come on since then. And we've seen perhaps a glimpse in the direction it might be going. That's all from me. I'm happy to try and answer any questions, but I doubt I'll be able to. So please please ask them if you fancy. Thank you very much. A bit terrified of this. I had a heckler who got me bang to rights on the LTE stuff. I had a mistake in that the other day, last time I did this. So.
Questions? Any questions?
Right. Please.
Radar was pretty much simultaneously developed in 6 or 7.
Yeah, I think you might have missed that. I did. Hopefully. I think I made that. Did I make that clear? Yeah. There we are. I thank you. Thank you.
Okay.
I thought I did. I'm sorry.
If there are no questions, so thank you to William. We hope you get on okay this coming week or 10 days in terms of your exams, and we hope the rain keeps off as you cycle back to Ipswich Station. And far more to the point, we hope greater angular behaviour will go on. So thank you again. A great talk, and William has promised me that he will come to the convention and with a different talk this year. So those of you going to the convention, please William some support. Thank you again, William.
Thank you.
It's nearly 1:10. If we take 40 minutes for lunch, if we can be back by 10 to 2, which gives us we're about 20 minutes to drink.